So, I've got this, looks like there's a kid sitting on a bathroom scale. And it tells us in the problem that we're trying to find the apparent weight. Now, the apparent weight, or the scale reading. Let's just talk about what that is really quickly. The apparent weight, let's make a little jot here. When somebody says that, what they're trying to say is the reading on the scale. And whether you've kind of like fully internalized this or not before, the reading on a bathroom scale is the normal force. In other words, the bathroom scale pushes up with that normal force. And that's what the reading on that little device is your normal force. So we're trying to find the normal force. And this person is sitting on a scale. The person has a mass of 50 kilograms. And their friend is pulling down on them with 40 newtons. Okay, fair enough. Now, what does that mean? That means that we have a little friend here, and they're holding on to our main character. And this little friend is sitting on the floor of the bathroom, I guess, pulling down on the main character. Let's put a little number 1 on our main character and number 2 on our secondary character. And I've lived this situation myself, having children. My kids are bigger than this now, but there were definitely times when I was just trying to do my morning routine and this little person pops up beside me and is like tugging on my sleeves or something like that. And so that's exactly what this is. We got somebody pulling down on us. And as we do this, let's give ourselves a reference frame. So I'm going to say up is positive and down is negative. And I think a smart thing to do would be to hash out a free body diagram. I know that I've got a force due to gravity acting down on person 1. I'll call it Fg.1. And wouldn't there be a force of 2 acting down on 1? Like in our little story here, this person's pulling down on their large friend. Force of 2 acting down on 1. And then what am I missing? Yep. Normal force. Yeah, there's a normal force. And I'm going to make it big. Force of normal acting on 1. And of course, one thing that we've said over and over again is that free body diagrams are just equation generating machines. So whatever this free body diagram is, it's equal to F net acting on 1. And what's more, we could take stock of all the numerical values. We could say, okay, well, mass 1, based on the descriptor there, is 50.0 kilograms. We could say, well, the person's probably on Earth, because it doesn't say otherwise. So 9.81 meters per second squared. And I can say down. That's just a little down arrow. And we could say, well, force of 2 acting on 1, according to the descriptor, is 40 newtons rather, which is also down. That little person pulling down on us. And, oh, what about the acceleration of the system? What's the acceleration of the system? Yeah, 0. Yeah, it looks like the total acceleration, the acceleration of this system, is 0 meters per second squared. Now, we've said in the past that we could say F net is equal to the picture. We've also said in the past that F net, according to Newton's second law, F net acting on 1 is mass 1 times acceleration 1. That's another way to find F net. In this situation, what's acceleration 1? 0. Yeah, look at that. Acceleration 1 is the acceleration of that system. It's 0 meters per second squared. Yes, sir?
If you put above apparent weight as force normal,
yes,
then couldn't we show that force normal here is 50 kilograms?
No, force normal is not 50 kilograms. There's 2 problems with that. One, force and mass are not the same thing. And the other problem with it is that if I have a force due to gravity acting down, which would be the actual weight, and our person pulls down on you as well, can you see that if the net force is 0, this normal force has to be counterbalancing those 2. So those are 2 flaws with saying that the normal force is 50 kilograms. Force and mass can never be the same thing. Definitely not. Okay, so we'll block this off just a little bit. And a little point of trivia, just since you asked that thing about weight versus mass and the confusion of the 2, let's just make a point to ourselves that the definition of weight, force of gravity, actual weight, not apparent weight, force of gravity acting on 1 is mass 1 times acceleration due to gravity, which we've done a lot of homework on recently even, right? Talking about weight. So weight and mass are definitely not the same thing, although I do need to know somebody's mass to calculate their weight. Okay, so thinking about this free body diagram as an equation machine, I would say F net 1 is equal to F normal 1 plus force due to 2 acting on 1 plus force due to gravity acting on 1. And as I look at this, there's something I can cross out and replace with a 0. What is the something? Yep. Yeah, F net. Look, if F net is mass times acceleration of the system and acceleration of the system is 0, then I'm going to make a logical leap here and say that that means that F net 1 is 0. That's why I'm making that logical leap. And I say, well, what am I looking for? Apparent weight. Normal force. Okay, so I'm going to say normal force acting on 1. I'll get that all by itself. I take the others over to the other side. Force of 2 acting on 1 becomes negative. Force of gravity acting on 1 becomes negative. And if I'm trying to find the normal force, I think I can sub in my values. I can say, okay, F normal acting on 1 is equal to, now this blue negative sign is because of the negative in front of force of 2 on 1. I want to make something really clear. I'm about to sub in a value. Force of 2 acting on 1 is 40 newtons, but it's 40 newtons down. What direction is negative? Down. So when I sub in this value, I'm going to color code it. I'm going to put in an orange negative sign just to point out that I have a reference frame, and that negative sign is coming from the reference frame. You don't have to color code it if you don't want to. I'm just being that way for my teaching right now, okay? When you do your work, you don't have to color code. Please don't. It'll be a waste of your time, okay? But we want to make sure we know why we're doing what we're doing. So force of 2 acting on 1 is negative 40.0 newtons minus, and again, that negative sign, the first negative sign is from the algebra. This next negative sign is from the fact that acceleration due to gravity is going to be down. So we know that force due to gravity is mass 1 times acceleration due to gravity. Actually, you know what? I kind of jumped the gun on that one because I'm about to sub in the mass, and the mass isn't negative. That would be silly to have negative mass. The mass was 50 kilograms. Of course, it's acceleration due to gravity that's negative, 9.81 meters per second squared. So that's where that negative sign is coming from. You notice that I've indicated which ones are my reference frame negatives and which ones are my algebra negatives. And I won't do that moving forward. I'm just doing it for now because we're still in the learning phases of things. And I do all my math, and I have total faith that you folks can do this. But can I get somebody to confirm with me that I do my math correctly? That's what you got? Okay. And then of course we can round this off to, it looks like we only have like 3 significant figures, so it looks like we'd have to round this off to approximately 5.30 times 10 to the power of 2 newtons, and we could say up. And we could write a therefore statement. We can say therefore the apparent weight on the scale is, the person's apparent weight is 5.30 times 10 to the power of 2 newtons. Now keep in mind, that is not their actual weight. If I wanted to calculate the actual weight, I would calculate Fg equals mass times acceleration due to gravity. This is weight. And I would plug in 50 kilograms times 9.81 meters per second squared, if I was thinking as acceleration, or 9.81 newtons per kilogram if I was thinking about gravitational field intensity at the surface of the Earth, and I'd end up getting 490.5 newtons. And as I look at this and I try to be sensible about this, doesn't it make sense that if I have a little friend pulling down on me, isn't the scale reading going to jump? Right? My friend pulls down on me, my actual weight's 490.5 newtons. The scale's going to read higher. This makes physical sense, right? And some people are like, well, wait a minute. I measure my weight in pounds. And if you didn't know this already, we're measuring weight in newtons. Pounds is a unit of force. It's a unit of force. Pounds is a unit of force. Pounds is not actually a unit of mass. And so if anybody's confused about that, that's the case. Pounds is a unit of force. You want to talk imperial units, British units, what the Americans use for weighing themselves. They use pounds, but that's a force. If you wanted to know mass, in that same family of units. Anybody know what it's called? It's a slug. You have slugs. Anybody ever say, they go to the doctor and say, you know, I was told that I was a little bit too round in the middle. I got to lose a few slugs. Nobody talks that way. But that is a unit of mass, an imperial. Okay, so just so you know, there are mass units and force units. Pounds is a force unit. Yes, sir?
Why is it 5.3 times 10 to the power of 2?
So there are 3 significant figures in this calculation, and so we're rounding it off to 3 significant figures, 530.
Why is it up if that's putting down?
Why is the normal force up? The normal force is up because that's the direction it's pointing in. And it's positive. It is definitely positive, so that agrees with our reference frame. Okay. Just a quick little side point. Yes, ma'am?
Why round to 5.30 and 530.5
Oh, that's a good point. Why didn't I round up to 531? So that was that funny little rounding rule. When it ends exactly in a 5 and no more, then you round even. And so it happens, and this doesn't happen very often, that we round to 530. If it was 530.51, we would have rounded up. So that tipping point issue with rounding, yeah. Then there is the other question about getting confused about mass and weight. And I want to draw your attention to this little graphic in the bottom corner here. This is a good way to talk about this. Oh, if I can just get it to focus, wouldn't that be great? There we go. So I've got a person, and this person has the same mass whether they're standing on the moon or on Mars or on Earth, because mass is how much stuff you're made out of. But when I go to the moon, my force due to gravity is small. When I go to Mars, it's less. When I go to Earth, it's even more. It's just to drive home the fact that weight is a force, whereas mass is a measure of how much stuff something's made out of, particle-wise, you know? So just drawing your attention to that, just in case you're getting confused about that idea. And I can understand, especially if you're somebody who has always been told that you were weighing yourself in pounds and didn't realize that pounds were a force, and now that's been a confused concept for you. I get it, okay? All right, let's take a look at somebody else who's in I won't say like less conventional situation, because this person is also a 50 kilogram person, and as far as I can tell, this might even be the same person. Maybe they got a haircut, they got dressed for work, they're on their way, and they're in an elevator now. Okay, you can tell by the briefcase. So if the same 50 kilogram person rides an elevator that accelerates at 2 meters per second squared up, let's say acceleration of the system is equal to 2 meters per second squared. And we can say that it's up. And you know, if I don't want to write the word up, I'll put a positive sign right now. And before we even do anything else, we'll define up as the positive direction and down as the negative direction. And then as I continue reading, oh yeah, it was the same person. So I'll just call it mass of person is 50 kilograms. What else do I know? Well, this person is probably on Earth. That's a reasonable assumption. So acceleration due to gravity is going to be 9.81 meters per second squared. Positive or negative? Negative. Let's throw a negative sign in front of that too. And good practice, if we want to know how much force is acting on their feet. Remember, that's what the bathroom scale was telling us, right? So this is kind of a bathroom scale situation minus the bathroom scale, right? So we're talking about how much force is on this person's feet. Same thing. We're finding the normal force. So we say, all right, well, there's a force due to gravity. There's a normal force. And that's going to be equal to F net. There's no side-to-side force. We're not trying to slide this elevator rider sideways. And so if I take that free body diagram, I can build an equation with it. F net is equal to F normal plus Fg. Notice there's only one person in this situation, so I'm not even specifying that it's F normal on person and Fg on person. I'm just going to say F normal and Fg, because it's only a one-body system, right? And if I want to get that F normal all by itself, I could say, okay, well then that means that F normal is equal to F net minus Fg. Just getting F normal all by itself. And now that I've got F normal all by itself, I think I want to sub in my values. Well, F net, we said not too long ago, F net is the mass of that object, in this case the mass of the person, times the acceleration of the person. Isn't the acceleration of the person the acceleration of the system? Well, let's say it that way. Minus Fg, which is mass of the person times acceleration due to gravity, because Fg is the actual weight of the person, force due to gravity. And we can sub in our values. We say, okay, well, the mass of the person was 50 kilograms. Acceleration of the system, notice I'll bring my givens back on screen here again. We said the acceleration of the system was positive 2.00 meters per second squared minus mass of the person 50 kilograms times the acceleration due to gravity, which we said was negative. Again, I'm emphasizing that this negative sign is coming from the reference frame, 9.81 meters per second squared. And again, I have total faith that you guys could do the math. Look, I got a double negative that's going to turn into a positive. And I just need some quick feedback. Did I do this right? I get 590.5 newtons. Agreed?
Yes.
All right. Now, in terms of significant figures and rounding, this one is going to round off to, for the same reason, because it ends in a 5 and nothing more. The rule is round even when it ends in a 5 and nothing more. And you're going to round away just the 5. We end up getting 590 newtons with the line over the 0 to indicate that it's significant. Or we could write it as 5.90 times 10 to the power of 2 newtons, just so we don't have any question about the ambiguity of that 0. Yep.
Will marks be taken off if we don't do the rounding rules that way?
Yeah, rounding mistakes are rounding mistakes. Errors are errors in baseball and physics. And we call that up, right? So the normal force is up. And of course, we can write a little therefore statement about this, absolutely. But you know, when I was a kid, I had a paper route, and I can remember my favorite part of my paper route was the fact that I had 4 paper routes, actually. And I would get up at 5:30 in the morning to deliver the Toronto Star. And I know that legacy media, so you know, not a lot of people have paper routes anymore. But I would get up at 5:30 in the morning, I'd deliver the Toronto Star, and my favorite of my 4 paper routes was the apartment building. A couple reasons. One, summer, air-conditioned, winter, heated. That's important. 2, high-density housing means lots of customers. And actually a third reason, it was mostly people that were of a retirement age, and some of their disposable income meant that they tipped better than my other customers. It was amazing. Everything about this place was amazing. But when I would have I had like a big bag that I would put over my shoulder, and you can imagine if you're sitting there in the elevator and there's a bag over your shoulder and there's a bunch of newspapers in that bag, when you start to accelerate in the elevator, isn't your shoulder going to feel more force? Because you're trying to apply more normal force, just like this person in the elevator, right? And I would feel that heavy bag of newspapers because I would have to supply the normal force. And so that's like a distinct memory for me. And if you've never been in that situation, that's fine. But I bet you've been in a situation like this where you're in that elevator. I know that you've been in this situation because I've been in that elevator with my own kids. And you're in the elevator and the acceleration of the elevator is upwards right at the beginning. You know when the engine kicks in? And you go up. And when you first start going up, you ever get the butterflies? Like little butterflies in your tummy, you know? Like a little tickly feeling. And I can always remember my kids would have that tickly feeling right there in their tummy. And it turns out that the inside of your tummy is kind of like a person being in an elevator, except your contents of your tummy is the rider. Can you imagine that the normal force increases on the contents of the stuff in your tummy? And that's going to send a nerve signal to your body saying, oh, something's happened. There's other cavities in your body. Your bladder. Turns out that there's a difference in the normal force pressing up on the contents of your bladder. Sends a nerve signal too. And so people say, well, I got butterflies in my tummy. Yeah, and in your bladder. And that's okay. And that little nerve signal isn't just because it makes children giggle. It's there because, can you imagine your ancient ancestors? Can you imagine they're just standing somewhere and the normal force on their bladder contents changes? What does that mean? Something funny is happening, right? Like, oh my goodness, the normal force on my bladder contents just changed. Am I being launched into the air? That's crazy. That could be deadly. If the normal force decreased, does that mean you're being launched or you're falling? You're falling. My goodness, the normal force on my bladder just changed and it decreased. I'm falling out of a tree. I'm falling off the cliff. You see where these butterflies are actually a survival thing, right? This is important. And we've tapped into that with amusement parks. And of course, there's like whole amusement parks where they take you all the way up to a tall, tall tower and you're all sitting around on seats like in some sort of a platform and they drop you down really, really fast. And of course, the whole purpose of that ride is to decrease the normal force on the contents of your bladder so that you giggle. And they've tapped into survival instincts and made it a ride. And it's all about the normal force. Really, on something that's traveling not in an elevator, but in a different chamber. But it's all the same idea. And we physicsed it. And that's important, okay?